Hello, this is Chemistry of Carbon and its Compounds, Part 2, Carbonyl Compounds in Detail. The assessment criteria for this podcast is as follows. You will understand and know the reaction of Toland's reagent and Fehling's Benedict reagent with aldehydes and ketones and understand their use in testing. You'll also know and be able to account for the products of oxidation and reduction of aldehydes and ketones. You'll understand and know examples of nucleophilic addition reactions of aldehydes and ketones. You'll be able to recognize carboxylic acids as weak acids and know their reactions with carbonates. You'll also be able to understand the esterification reaction and the hydrolysis reaction, recognizing these two reactions as equilibrium reactions, and be able to determine the appropriate conditions using equilibrium considerations. And you'll also be able to know some uses of esters, including flavorings, natural esters, soaps, and biodiesel. The first assessment criteria is to know the reactions of Toland's reagent and Fehling's Benedict's reagent with aldehydes and ketones. Aldehydes readily undergo oxidation in air to form carboxylic acids. We saw this last year when we talked about alcohols. Ketones are much more resistant to oxidation. The Toland's test, or the silver mirror test, using the Toland's reagent, a combination of silver nitrate and ammonia, is used to test for an aldehyde. When Toland's reagent is added to the suspected aldehyde, the silver ion is reduced to silver metal if an aldehyde is present. The silver metal happens to deposit on the inside of the test tube, and it gives a mirror effect to the test tube. The use of Fehling's or Benedict's solution is similar to the Toland's test, but instead of the silver ion, the Cu plus 2 ion is reduced to Cu plus, which precipitates from solution as Cu2O, a brick red solid. Benedict's solution was once used for glucose urine testing strips for those people who have diabetes. The preferred method now is not to test the urine, but to test blood glucose, and a different solution rather than Benedict's solution is used. Let's take a look at that silver metal deposit, the silver mirror test, in a video. The second assessment criteria is to know and be able to account for the products of oxidation and reduction of aldehydes and ketones. Aldehydes and ketones are easily reduced by hydrogen gas in the presence of a catalyst, nickel, platinum, or copper, to form alcohols. The reduction of aldehydes yields primary alcohols. The reduction of ketones yields secondary alcohols. You can see in the picture there that equilibrium situation. This process is much like the addition of hydrogen to the carbon-carbon double bond of an alkene to produce an alkane. Understand and know examples of nucleophilic addition reactions of aldehydes and ketones. In order to do this, we need to look at the carbon-oxygen double bond. The carbon-oxygen double bond is electron-rich and highly polar at the oxygen end. So nucleophilic addition happens with an electron-rich group bonding to the carbonyl carbon and an electron-poor group bonding to the carbonyl oxygen. If you look at the mechanism, that mechanism looks familiar. It is a carbocation. Notice the carbon on the double bonded O has a positive charge and attracts, in this case, the cyanide electron-rich atom. And it is completed by the addition of a hydrogen ion from the hydrogen cyanide molecule to make the alcohol. Nucleophilic substitution, carbocation. Carboxylic acids are weak acids, and they do react with carbonates. Let's think about our definition of acids. One of the definitions of acids, a Bronsted-Lowry definition, says an acid is a substance that donates protons or hydrogen ions to other things. And the carboxylics are weakly dissociated. In a solution of water, a hydrogen ion is transferred from the COOH group to a water molecule. You can see that equation below. With carbonates and hydrogen carbonates, a salt is formed together with carbon dioxide and water. So, in this weakly dissociated atom, if we add a carbonate or a hydrogen carbonate, we get H2O and CO2. You can see that in the two equations there. Know the esterification reaction and the hydrolysis reaction, and recognize these as equilibrium reactions, and determine the appropriate conditions using equilibrium considerations. Esters are produced through the esterification reaction. It's a catalyzed reaction, usually using sulfuric acid as the catalyst, between a carboxylic acid and an alcohol. An OH group is lost from the carboxylic acid, and a hydrogen atom is lost from the alcohol, and water is formed as a byproduct. That is the esterification reaction. Esterification reactions are equilibrium processes, with the position of the equilibrium favoring products only slightly. How do we increase the rate of products? Well, Le Chatelier's principle tells us to use an excess of alcohol to push the reaction to the right, or by constantly removing the ester from the products to encourage the production of products. Know some uses of esters, including natural esters, soaps, and biodiesel. Flavorings and fragrances of fruits and flowers are largely caused by esters, with more than one particular ester being dominant. It's interesting that some esters are very close in structure, but very different in flavor or smell. The only difference between the apple ester and the pineapple ester is one carbon atom, the difference between a methyl and an ethyl group. A number of pheromones contain ester functional groups. The alarm reaction of honeybees is created by a pheromone, and sexual attractants for dogs are also ester pheromones. Numerous esters have medicinal value. Benzocaine is a local anesthetic. Sometimes you rub it on your skin when you have been bitten by a bug. Wintergreen and aspirin are both esters of salicylate acid. I have a video here that describes some natural esters other than the ones I've just mentioned. Take a look.
Bananas and lavender. Pineapples and perfumes. Like many other sweet-smelling substances, they owe much of their pleasant aroma to chemicals called esters. Esters are organic compounds produced by a reaction between an alcohol and a carboxylic acid. They are made of a sequence of carbon and oxygen atoms known as an ester linkage. They're widespread in nature, but they can also be created in laboratories by reacting two ingredients in the presence of a sulfuric acid catalyst. One of these ingredients is an alcohol, like methanol or ethanol. The other is carboxylic acid, like ethanoic acid or butanoic acid. What is surprising about carboxylic acids is that they have sour and disagreeable odors. Yet when combined with alcohol to make esters, they create lovely smells. For example, butanoic acid gives rancid butter its putrid smell, but the ester it makes with ethanol has the scent of pineapple. The ethanoic acid, which gives vinegar its pungent whiff, combines with different alcohols to create the aromas of pears, bananas, and citrus fruits. Esters are widely used in manufacturing, particularly in the perfume industry. But as well as having an appealing smell, perfumes need other qualities to be commercially successful. To be used safely, they need to be non-toxic and must not irritate the skin. And so they don't wash off easily or react with sweat. They need to be insoluble in and rather unreactive with water. And for the scent to reach the nostrils quickly, the compounds in the perfume need to be volatile so that they evaporate easily. The fragrant properties of esters are also exploited in the food industry, where they're used as flavoring agents. Without esters, the scent of the world around us would be very different and much less pleasant.
Here's some questions to start your thinking. They're on carboxylic acids and esters. I'd like you to answer these questions and produce them for me when asked. Looking forward to seeing you next time.